Hi there. This is a presentation over Chapter 2, Heating the Earth's Surface and Atmosphere for Floyd Central High School students in meteorology, a dual credit course for Science 111 on a college transfer list. Our goal with these broadcasts is to function a greater detail on labs in our face-to-face class. So what we can do is take our traditional lecture and our traditional information content presentations and put those in a more flexible capacity so that students can retrieve those through YouTube. And as we transfer through a migration of kind of a bring your own device technology or a unified technology, then we can have a resource out there that is web-based so that students may have their traditional lecture content but have a greater focus of lab-based experiences in class and a greater individual focus in class. So let's dive in. We've got 5 objectives over this session. And what we're going to do is work through this in an abbreviated sense and expand on it in class a bit and then practice with it in class even more. So our 5 learning goals within this presentation are seasons and seasonal effects, energy, temperature, and heat relations, methods of heat transfer, fate of solar radiation, and the Earth's energy budget. And what we'll look at here is first the seasons and seasonal effects. What is it that causes the Earth's seasons? Hopefully we can recall sometime in the past we were told that the reason that the Earth has seasons is because of the tilt function. The Earth is tilted at 23.5 degrees, and that is the chief reason, that is the chief effect of seasons. There are 2 terms that deal with seasons that get confused, and that is rotation and revolution. The Earth's rotation deals with the spin on the axis. The Earth's revolution deals with a motion of a planet like the Earth around a larger object like the sun. So the function of rotation is day and night. The Earth rotates on its axis and it causes us to notice the sun rise and set. We see the sun trace across the sky hour by hour, and it moves in about 15 degrees. It moves in about an hour, about 15 degrees. Revolution is the process of a year. So we keep track of time in regards of an annual process by the path of revolution. So months change every 30 days or so as the planet revolves around the sun into a different set of stars. So astronomically, we've used this for quite some time because we can see the migration at night of certain groups of stars into and out of our night sky. So seasonally, a function of revolution is a year's amount of time. There are 2 things that we need to understand from a revolution perspective. The Earth is at a point that is the closest and at a point that is the farthest each lap that it takes around the sun. When the Earth is the closest to the sun, it's referred to as perihelion, and helios or helion being in reference to the sun. So when the sun is the closest to the Earth, it is perihelion, and that occurs during January 3rd. And that's not a misprint. January 3rd seems like it should be a warm time of the year for the Northern Hemisphere. So we must have something that's a fairly powerful moderator of season in effect during January 3rd if our planet is the closest to the sun, but is still cold. And that is a function of tilt. So even though we are closer to the sun in January than we are July, it is still cold for North Hemisphere occupants because we are tilted in the Northern Hemisphere away. Our angle of incidence is tilting the Earth's Northern Hemisphere away. So it's an angle that doesn't change, but it is depending on how it's correlated to the sun. And we'll look at some diagrams to reinforce that. On the other side of the seasons, we have aphelion. Aphelion is when we are the farthest away. The Earth is farthest away. And it seems like that would be cold, but it's not. It's during a warm time of year. And the reason being tilt again. So even though we are farthest away from the sun during July 4th, we are warmest because this is when the Northern Hemisphere is tilted toward the sun. So 4 terms here that get interchanged and mixed up incorrectly quite often during this part of the course. And I would really encourage you to work on making a strong connection to those and being able to use those in an essay response, in a diagrammatic response, in a labeling form. Rotation versus revolution. Rotation is spin, and it's 24 hours, 23 hours, 56 minutes, and it deals with the day and night. Revolution is orbit. It takes a full year, and we see a drastic difference. With revolution, we have two terms that get confused, perihelion and aphelion. Ap is away. Aphelion is the furthest distance between the Earth and Sun, and the reason it's warm is because the northern hemisphere is tilted toward the Sun. Perihelion is when we are the closest, and the reason that's not warmer is because the northern hemisphere happens to be oriented away from the Sun. So our tilt doesn't change. It's always 23.5 degrees. It's an orientation value. So when we look at diagrams like this and we see the Earth-Sun relationships, we can see where the Sun is during our solstice, and we can see where the winter season is during its solstice. So we see these types of relationships, and they are certainly a relationship to be noticed with incoming solar units, which is the goal of the column of diagrams on the far right hand of the slide. So when we see images that show incoming solar units, and those solar units are plentiful, like in the diagram with the palm trees, we see a great deal of heating. When we have scarcity with the solar units, like in the example with the igloo, we have a much cooler day. So it may be surprising that the column shows the same time of year for all of these locations. The palm trees is summer. The barn and the silo is summer, and the igloo is summer. Neither one of those will feel equally as warm because the amount of solar units is not the same. And it deals with a solar altitude discrepancy. And that solar altitude discrepancy will be studied numerically in class. What causes the seasons? Well, ultimately it's tilt. What we do notice is there is a gradual change in day length that causes some of the seasons to occur. And that doesn't mean that that's the sole reason, but the tilt of the Earth, which is then causing a change in day length, then causes us to reflect into a seasonal change. That change of the angle of the Sun plays a significant role. So seasonal changes are connected to changes in daylight and changes in altitude of the Sun. Altitude of the Sun is similar to what we studied in our astronomy class with the declination of stars. The difference is stars at night is declination, Sun during the day is altitude. Moving into this orientation depiction. Look carefully at the diagram at the lower right. You have several different latitudes that we need to understand. There's about 5. We have the equator, Tropic of Cancer, Tropic of Capricorn, and Arctic Circle that we need to concentrate on in different positions during seasonal positioning. So we have our solstice seasons, we have our equinox seasons. Please read those sections of your textbooks carefully. What we're talking about there and what the author expands on and most classic introductions deal with is the striking of sun's rays, the incidence of the sun's rays upon a specific latitude, like we see in the Earth diagram to the left. When the sun's rays strike a particular latitude directly, a 90-degree angle is formed. When that 90-degree angle is formed, we are at a particular season. So while we have the 23.5 degrees south latitude, which is the Tropic of Capricorn, with the sun directly over it, that would be the winter solstice, which would be during the dates of December 21st, 22nd. So what we can do is use the sun to tell time. When we are at 23.5 degrees south latitude and the sun is directly over us, we know we must be close to December 21st, 22nd. And that would change if we were in the North Hemisphere. We will practice on those concepts and reinforce them with lab and practice exercises in class. Moving on, we have particular dates that were mentioned in the last slide. Please work on committing these to memory. We have June 21st, 22nd, December 21st, 22nd for our solstice, summer solstice and winter solstice respectively. We have specific latitudes that we need to understand, not only the numerical value of, but the names of. Tropic of Cancer in the northern hemisphere, Tropic of Capricorn in the southern hemisphere. Both are 23.5 degrees latitude. That creates a 47-degree latitudinal band of the tropical regions of the planet. So what we see there is a ability of the sun to be directly overhead within a net of 47 degrees latitude. Areas geographically outside of that range do not have the capacity of experiencing a sun angle at 90 degrees. We have fall equinoxes that occur at the respective dates, and then spring equinox, which have a vernal connection as well. So we see those, and that's where we have the equator. An easy statement that helps the equator, equinox, and equal amounts of daylight is that during the equinox, the sun is directly over, which is a 90-degree angle, the equator, and that creates equal amounts of daylight and darkness. Moving on into solstice and equinox. These diagrams that you see will be reinforced with a lab that will not be overly technical in class, but we will work on determining the amount of daylight from latitude and the circle of illumination. You see the circle of illumination in each one of these diagrams. The circle of illumination is simply the difference between daylight and darkness, like a shadow. So when we see in subset A, the June solstice, at 66.5 degrees north latitude, it is no surprise that that entire line, that light white line there, is in daylight. Therefore, they have 24 hours of daylight. Let's compare that to 66.5 degrees south latitude. We have no part of that line in daylight. Therefore, they would be experiencing 24 hours of darkness. You might observe the sun right below the horizon, but it will not be over it. So we have parts of the planet that do experience 24 hours or 6 months of daylight and 6 months of darkness. That's why we refer to them as land of the midnight sun. We will reinforce these concepts further through lab and class. Forms of energy, moving into energy, temperature, and heat. Energy is the ability to do work. We have two types of energy we will recognize in this class, potential and kinetic. When we have kinetic energy, we are measuring energy of motion. Potential energy is energy that has capacity to do work. When we measure temperature, we are measuring kinetic energy. So as energy is increasing, temperature increases, the molecular motion of atoms is also increasing. As temperature decreases, energy is lost. So when we have an increase in energy, we have an increase in temperature, in kinetic energy. Heat is the ability to transfer energy in or out of objects due to temperature differences. Heat will transfer from hot to cold objects, and we've all experienced the difference of change of this energy. Certain things are better conductors than others, but we can have energy that goes into an object, but the temperature not change, and that's called latent heat. So when we have a latent heat in effect, we have energy absorbing, but no increase in temperature. We will sample some of those concepts in class through lab. Sensible heat is quite intuitive. When we have sensible heat, we have an immediate change, and we can feel that change. Conduction, convection, and radiation are all mechanisms of heat transfer. Conduction is a heating through direct contact. Convection, we have a heating through a fluid or an atmosphere or a movement of circulation of a substance. We're going to connect to water vapor specifically in this course with convection. And many of you are familiar with the convection ovens in your homes. When we get into radiation, we have to consider, again, like we did in astronomy, the entire electromagnetic spectrum. So recall or understand that we can only see 4/10 to 7/10 of a micrometer. And there is an inverse relationship with energy and wavelength. Notice to the far left of the spectra that you have the smallest wavelength. Wavelengths are really close together lines. That is highly energized material. When we move to the right of this, we have an expansion of wavelength, and that is less energetic. Therefore, radio waves at the upper right are less energetic than ultraviolet. X-rays are more energetic than ultraviolet. Gamma rays are more energetic than infrared, and we can see those organized well. This is also where we get our acronym ROY-G-BIV. ROY-G-BIV stands for the colors in front of you: red, orange, yellow, blue, indigo, violet. and you can see how it's inversely proportional. So we have to mentally recall that rho e.g. Biv is a representation in a backward, kind of a mirror view sense. Radiation travels through space like some things, but unlike others. Wavelengths are described by crest to crest. That would be the peak of those waves. But the thing that's different about solar radiation, it doesn't need a medium to travel through, where the sound that you're listening to does need a medium. So solar radiation is fairly intense in some regards and more docile in others. But it is amazing that we can feel the solar radiation that we do from 93 million miles away. So that gives an indication of how energetic it is. Visible light is often referred to as a compendium of light, of white light. Infrared radiation is beyond the red and it's less energetic. You and I are giving off radiation in the infrared in the form of body heat, and ultraviolet radiation is intense, much more intense than infrared. There's a handful of radiation laws we'll connect to in this course. This will be much less specific than what we dealt with in astronomy. This is the work of Planck, Stefan Boltzmann, Wines. Those gentlemen in the late 1800s, early 1900s were doing groundbreaking work with radiation, and they noticed that as temperature changed of a metal or of a substance that didn't burn, didn't change state quickly, that the color changed. And as it got hotter, it got brighter, or it changed colors. So many of you have seen examples of this. We just make a more direct connection to it in a course like this. So these are the 4 laws of radiation that we'll work with. All objects will emit radiation, whether or not they're animate or inanimate. Hotter objects will radiate more total energy than colder ones. So it's not uncommon to see a stove burner become red once it begins hot. The hotter an object is, the more shortwave radiation that it forms. So as we continue to heat that burner, if it gets ultimately hotter, it may change from an orange to a red. And then if we continue to heat it, it may go to a yellow to a white. Objects that are good absorbers of radiation are good emitters. So if we have an object or we have a substance and we have an industrial use for it and it's absorbing energy quite well, it should, in theory, emit that energy nearly as well. What happens to the insulation or the energy as it enters the Earth's atmosphere from the sun? It has several different fates. 3 of them are here. It's either reflected, scattered, or backscattering. Reflection is the return to radiation back to space. Scattering produces these types of events that we're used to seeing in the Earth's atmosphere that we'll talk about shortly. And backscattering is where we have a more vague scattering event. So when we look at specific instances here, one of the things we need to dive into with reflection is a concept called albedo. It's the percent of reflectivity or reflected light from a surface. When we look at the moon being gray and very volcanic rock and pulverized dust, regolith, we get into about a 7% albedo. So only about 7% of the sun's light that strikes the moon gets returned back. It's not overly bright. The Earth, on the other hand, about 30% of that sunlight that strikes the Earth gets returned back to space. So we are considerably more bright. Our planet is considerably more bright than our moon. One of the most reflective substances on this planet is snow and ice. Then we move into water. Moving on into the next slide, we can see how the incoming solar units from the sun fare. 50% of these are direct and diffused radiation, and they are absorbed by land and seas. About 20% are absorbed by our clouds. 5% become reflected from the surface, and about 5% is backscattered. It never really makes it to the surface and does very little good to heating in lower atmospheres. The lower atmosphere has a further division. We can see how light roofs and dark roofs have a different disparity. So the light roofs will return that energy back to the atmosphere, depending on the covering. Agricultural, plowed fields versus wheat fields, green grass versus a dry season, brown crispy grass, sandy beach, water. We all have different divisions of this. So there is a lot of intuition that goes into play here. Most of you are aware of the fact that white colors will reflect more light and dark colors absorb those. That rule goes to effect with this concept as well. Moving on into the next slide, let's talk about diffuse light. This is a bit more vague. This is a result of dust particles or suspended aerosols in the atmosphere, and they scatter light in different directions. This results in clear days with bright blue skies. Sometimes in the wintertime, you can notice how we have clear days, and in certain seasons, we have a lighter blue sky with no clouds, and in other seasons, we have a brilliant blue sky with no clouds. And the difference is diffuse light. So when we have more particles in the atmosphere, it steals away from the brilliancy of our blue sky. When we have less suspended particles in the atmosphere, we have a gorgeous blue sky. Red sunsets, and sometimes we can see a magenta sky. These are a function of radiation as well, and we will explore those later. Heating of the atmosphere. One of the things that we can look at with Planck's work, with absorption, with Wien's work, is an amazing consequence of our sun and the visible radiation. So it happens to be that the light that you and I need to see is the peak radiation amounts from the sun. So our sun does an excellent job emitting the light or energy that you and I need most to see, which is amazing for us as far as the capacity to survive on this planet. Some of the gases you notice here, they absorb energy quite well. So some of our gases are good absorbers of certain wavelengths, and they're terrible absorbers at other wavelengths. Notice how much water vapor absorbs. Also check out oxygen and ozone. Some of these do a really good job absorbing certain wavelengths and not others. Oxygen and ozone do a nice job of absorbing UV. Where you look at water vapor does a better job of absorbing more toward the longer wavelengths, and carbon dioxide. So carbon dioxide does a good job of absorbing longer wavelengths as well. But look at the water vapor. Notice how much more capacity water vapor has of absorbing longer wavelengths as compared to carbon dioxide. That is why water vapor is such an important greenhouse gas, especially like we mentioned in chapter 1, when it ranges from 0% to 4%. Carbon dioxide at 0.04% just doesn't have the atmospheric effect, but we are responsible as a species of releasing more carbon dioxide unnaturally. So we do watch that. So some of these are promoting what's known as a greenhouse effect. You're familiar with the greenhouse effect. This has been around for quite some time now, and it has a lot of intuition in it, but do make sure that we understand that it is not global warming. We do not want to stop the greenhouse effect. The greenhouse effect allows this planet to stay warm. Our average temperature is maintained in part by the greenhouse effect. In other words, we need greenhouse gases. Global warming is adding too many greenhouse gases and then causing the planet to warm up uncontrollably or unusually fast. And that becomes a problem, especially when we humans might be the cause agent of that. So do make sure you can differentiate between greenhouse effect, how water vapor, carbon dioxide, and other derivatives of greenhouse gases are able to help us maintain a warm planet, and how greenhouse effect is not global warming. Moving on, looking at the role of gases in the atmosphere, we understand, hopefully, that in this slide, the red lines are long wave radiation and the yellow lines are short wave radiation. So we have short wave radiation coming into the planet through the atmosphere from the sun. It strikes the ground absorbs that radiation, and then that radiation gets re-emitted back to the atmosphere through longer waves. So short wave radiation comes to the planet from the sun. The Earth absorbs it and returns some of that heat back to the atmosphere in the form of long wave radiation. So you and I can walk on blacktop and sandy beaches and feel our feet quite warm during the summertime. Annual energy balance is what we'll close with. We can see this annual energy balance being a function of latitude and heat balance. And we can also see how we have certain materials that are playing certain roles within this balance. So predominantly the clouds are the greatest controller of energy in the lower atmosphere at the surface. We've all experienced cloudy days where we don't get that direct sunlight and it makes it more cool, even on a wintry day. And when those clouds break, it's an amazing difference what that direct solar radiation can do. Similar to that of latitude, 38 degrees is a balancing point on the planet, and this is both north or south latitude. We live, Floyd Central, Floyd County, is right at about 38 degrees north latitude, which happens to be the point where incoming and outgoing radiation are well balanced, meaning the same amount of energy that comes in to Floyd County leaves Floyd County, meaning resulting in a very well balanced energy situation. This concludes our Chapter 2 presentation. Thank you for listening. We will work on these concepts further in our face-to-face session, and we will have a handful of slides that will most likely be different than these that are posted. So the goal being that you have two types of PowerPoint to look at to reinforce material from different perspectives. The subjects will be the same, but the PowerPoints that are posted online through the web page and that are used in these presentation series will be different from those that are used in class. We will use a minority of PowerPoints in class and really concentrate on expanding that time and committing that time, that face-to-face time, to practice, labs, and reinforcement of these concepts so you can achieve a higher understanding of these materials. Thanks for listening. See you in class.